Now let's do one example from change of enthalpy H. So this is the problem statement that we have. We have air undergoing a change of state from 100 kPa and 33 degrees C to 800 kPa and 415 degrees C. The question is asking for the change in enthalpy of air by considering this equation of state, and also the value of A is given here. And at the end, the question is asking to make a comparison with values from ideal gas equation of state. So ideal gas equation of state is PV is equal to RT. Okay, so in order to solve this problem, I'm gonna utilize one of the correlations we had in another video about the discussion we had in enthalpy, and this is the equation that I am going to use. So I'm going to use dH is equal to Cp dt plus the rest of the equation, this one. All right, so the equation is dH is Cp dt plus V minus T multiplied by partial V partial T for constant pressure dP. That is the equation that I have. Now, in order to obtain the value of Cp, you can use table A2. Okay, so if you go to table A2, one thing that you observe is obviously Cp, or specific heat at constant pressure, is changing with temperature. So this is table A2, and the table reads ideal gas specific heats of various common gases. And in this portion of the table, we have it for air. So this portion is for CO2, CO, hydrogen, nitrogen, and oxygen. So we want to deal with here. So we are interested in this column, and you will see Cp is obviously changing with temperature. And we learned that back in Thermo 1, because we know that in ideal gas, specific heats are function of temperature. But in this equation, if my temperature changes from 33 degrees C to 415 degrees C, then my Cp is also going to change. So what I'm going to do, I'm going to calculate an average temperature and read the Cp value at that average temperature. So my T average is going to be 33 degrees C plus 415 degrees C divided by 2, which is 224 degrees C, and converting that into Kelvin is 497 Kelvin. So that is my average temperature. Now, in the same table, table A2B, I would read Cp value. Table A2B, I would read Cp equal to 1.029 kilojoule per kilogram Kelvin. Right? So I am kind of done with this, but I need to do something for this part as well. So the equation of state is given in the problem, and that is P multiplied by V minus A is equal to RT. This is given in the problem. What I'm going to do, I'm going to solve this for volume. So if you solve this for volume, that gives you R over P multiplied by temperature plus A, and the value of A is given. Okay, the reason I did that, the reason I solved that for volume is because here in the bracket I have volume and then partial V, partial T. So right now I can easily calculate partial V, partial T for constant pressure, right? Partial V, partial T for constant pressure is going to be R over P. So I can get into this equation, the main equation. So let me call this one 1 star. So if I go to 1 star, I can just plug in the numbers, because DH is going to be basically Cp. I have the value of Cp, which is 1.029 kilojoule per kilogram Kelvin. Okay, multiplied by dt, which is the change in temperature. So the temperature, the unit of temperature here is in Kelvin. But for this dt, it doesn't matter if you do in Kelvin or in degrees C, because we are looking at the difference of temperature. So I just go with 415 minus 33 Kelvin, although these temperatures are not really in Kelvin, but the difference of that is in Kelvin. Plus, okay, now V minus T, partial V, partial T for constant pressure, I need to do some math before plugging in. So this will give me V, maybe instead of V I could easily put R over P multiplied by temperature plus A. So let me just do that. So this is going to be R over P multiplied by temperature plus A. So the whole thing is my V minus T multiplied by partial V partial T. And I have it right there. R over P. So that gives me, this one cancels that. That just gives me A. So the entire bracket is A. So if I'm rewriting this here, because this equation is coming from equation 1 star, my entire bracket is A, and the value of A is given, that is 0.01 meter cube per kilogram. Okay, multiplied by change in pressure, and the pressure changes from 100 kPa to 800 kPa. So the delta P is 800 minus 100. 800 minus 100 kPa. Okay, so if you do the math, it will give you dH is equal to 393.07 kilojoule per kilogram, but that's for the first term, and the second term gives you 7 kilojoule per kilogram. All right, so at the end of the day, your dH is going to be 400.07 kilojoule per kilogram. Okay, so that is the change in enthalpy. Now, the question also asks for a comparison with the ideal gas law. If I want to do that, the ideal gas law basically in ideal gas equation of state, dH is equal to Cp dt. That is what we have in ideal gas equation of state. Well, the ideal gas equation of a state is PV equal to RT. All right, so this is ideal gas equation of state, but in ideal gas, this is what we have. So this applies to ideal gas. So basically, by doing so, my dH is going to be, Cp value is 1.029 kilojoule per kilogram Kelvin, multiplied by change in temperature, which is 415 minus 33 Kelvin. Okay, so dH is going to be 393.07 kilojoule per kilogram. Basically, the very first term that we already had here is change of enthalpy for the ideal gas. This is something special that comes from this equation of state. Okay, so at the end of the day, this delta H is for ideal gas, and this delta H is what we have for this particular gas.